Today we begin the unit on actually solving exponential and logarithmic functions. We're going to start with the equivalent forms of exponential functions, which we're going to see is a very powerful tool to solving things, whether it's pencil and paper or graphically, but mostly pencil and paper. The idea behind it is if you can express both sides or every part of the equation with the same base, everything is much, much easier to work with. So let's take a look at how that works now. For question 1, I've just said express each of these expressions as something with base 2. So the first one, 8, well, I will admit 8 is a pretty easy expression to work with. It's literally just a number. But I'm going to point out that it can be written as 2 to the power of 3. I'm also going to point out, and you'll see why in a moment, that I can rewrite this up here as an exponent with 1. 8 to the exponent of 1 is the same thing as 2 to the exponent of 3. Well, 4 to the exponent of 3 could be written as 2 to the exponent of 2 to the exponent of 3, which our exponent rules say is equal to 2 to the exponent 6. So 4 to the exponent 3 is equal to 2 to the exponent 6. For part C, this one looks a little bit trickier because it is a little, well, few extra steps. But I want to write 16 as a power of 2, and that's just 2 to the power of 4. But since I'm taking the square root of that, that's actually going to be to the exponent 1/2. And then for my 32, 32 is 2 to the exponent 5. And that's to the exponent 3. Sorry, actually, we got to do the fifth root first, so that'll be to the exponent 1/5. And then that whole thing is to the exponent 3. So now we can use our power rules to say that the first one is 2 squared. And the second one is 2 to the 5th to the 1/5, which is just 2 to the 1 to the exponent 3, so that's 2 to the 3. And the whole thing's equal to 2 to the exponent 5, which I think you can agree looks way prettier than the original expression that we were given. Okay, for part D, 12. How do I write 12 as a power of 2? Well, I'll give you a hint. In a question like this where it doesn't work out nicely, we learned a tool last unit to be able to express things differently. So what I'm saying is I want 2 to some exponent to equal 12. What can I do to both sides to actually solve that and figure out what the x is going to be? Well, an unknown exponent calls for logarithms. So that's going to be log of 2 to the x equals log of 12. And now my power law for logarithms says that I can bring that x in front. And finally, I can divide both sides by log of 2. So now I just pull out my calculator and punch in log of 12 divided by log of 2 equals 3.585-ish. And so really I can say that 12 is equal to 2 to the exponent 3.585. And there I've written a really nasty number as a power of 2. Is that prettier than 12? Not really. But if I'm dealing with a whole bunch of things that have different bases and I can convert them all to the same base, in this case I've converted all these different expressions to base 2, then they're easier to work with. Something else I want you to note is that really all we're doing here is saying we can change the base by modifying the exponents. In part A, we changed an 8 to the exponent 1 to a 2 to the exponent 3. We changed bases by modifying the exponent. And then we did 4 to the power of 3 is the same thing as 2 to the power of 6. Change the base, modify the exponent. And that's going to let us solve a lot of problems if we could change everything to the same base and then just play with exponents. So let's solve a question like number 2. And these are ones that we could do graphically, but we're actually going to do by hand because they're not actually that bad. Now, I'm going to point out that both 4 and 64 are powers of 2, so you're more than welcome to do powers of 2 on these. I will, however, point out that 64 is also a power of 4, so we could just keep the 4 base on the left-hand side and change the base on the right. So I'm going to leave that as x plus 5. And on this side, I'm going to say 64 is equal to 4 times 4 times 4, or 4 cubed, to the exponent x. So 4 to the x plus 5 equals 4 to the 3x. Now that I've gotten that far, I can see that both sides have the same base, which means they should have the same exponent. And if they have the same exponent, then I can just look at the exponents and say x plus 5 equals 3x. Subtract x from both sides, and divide both sides by 2 to get x equals 5 halves. Okay, so we did that by putting both sides with the same base by modifying their exponents. For part B, we can try to write 8 as a power of 4. Unfortunately, it's not a very good power of 4, but I can note that both of them are powers of 2. So I can rewrite 4 as 2 squared to the exponent 2x, and 8 as 2 cubed to the exponent x minus 3. Now, ironically, from here on in, it's mostly just simple algebra, but for some reason, people always kind of mess this one up. It's like they forget bedmass and how multiplication works. This side is going to be 2 to the 4x, and the right side is going to be 2 to the 3x minus 9. Almost always see people expand that one out to be 3x minus 3, forgetting the 3 affects the entire x minus 3 binomial. Okay, now that we have both sides with the same base, we can set the exponents equal to each other and say that 4x equals to 3x minus 9. Subtract 3x from both sides, and x equals negative 9 is our answer. That wasn't too bad. Of course, there's got to be some more tricks to learn, otherwise this would be a boring lesson. So let's look at a couple tricks here. For question C, 5 times 2 to the x minus 2 equals 40. A lot of people are going to try, I've seen students on tests try to convert the 5 to base 2 and the 40 to base 2, which is possible with logarithms, but horribly ugly, missing out that the super obvious thing to do on both sides is just divide by 5. When you do that, you get 2 to the x minus 2 equals 8. And now you can write this as 2 to the x minus 2 equals 2 cubed. So x minus 2 is 3, and x is 5. Again, I'm not sure why it happens. People forget the basic math when they're trying to do the more advanced math, but division by 5 on both sides makes this a lot easier. All right, part D. These are the ones that are usually done really poorly on tests. Because again, people forget how exponents work. There's a couple of ways you could do this. I'm going to show you what I think is a nicer way of explaining it, but not necessarily the shortest way. And you remember that if you're multiplying 2 exponents or 2 powers with the same base, then you add exponents. Well, I'm going to undo that here, and I'm going to rewrite 5 to the x plus 3 as 5 to the x times 5 to the 3. And I'm going to write the second one, 5 to the x minus 1, as 5 to the x times 5 to the 1. Okay, so what's the advantage to that? Well, the advantage is I've got a 5x in both of those terms that I can factor out. So I get 5 to the x, and once I factor that out, I'm left with 5 cubed plus 5. equals 200. And then inside the bracket there, I can say 5 to the x is 120 plus, 125 plus 5 is 130 equals 200. And now, unfortunately, this is not as pretty as I'd like it to be, but that's okay. We can do 5x equals 200 over 130. 5 to the x equals 200 divided by 130 is 1.538. And then at this point, I can use logarithms on both sides. And I'm going to take the shortcut on this one because we did one of these just above. But the x is going to equal to log 1.538 over the log of 5. And when we punch that into our calculator, we get out 0.267 roughly. And if you want, you can always plug that number back in for the x, do a left side, right side check and verify that it's true. If you plug it in on the left side, you get, well, when I did it, I think I got 199.8-ish. And I think the difference is just because, unfortunately, we had a little bit of rounding error there and a little bit of rounding error there. But either way, it's pretty close. So now I'm just going to point out really quickly the other way I could have done it, and I won't bother finishing it the other way because it's essentially the same method. I could have noticed that both of those have a 5x plus 1 in them and just factored out 5x plus 1. And that would leave me with 5 squared plus 1 equals 200. And then divide both sides by 26, solve for x plus 1, and your answer would be 1.267, subtract the 1 from both sides. So you could do it that way. You could factor out a 5 to the x plus 2, and you'd be left with 5 plus 1/5. Whatever makes it easier on you. I like to just take the power of x by itself and not have to worry about, a plus 1 or minus 2 or anything like that. So it's completely your call, though. For question 3, we have an exponential function, f at x equals 256 to the exponent x. Write an equivalent exponential function with each base. Okay, well, we know that, or we can figure out fairly quickly that 256 is equal to 2 to the power of, this is where I literally pull out my fingers and say 2, 4, 8, 16, 32, 64, 128, 256, and it's 2 to the 8. So what that means is I could write f at x equals 256 to the x as 2 to the 8 to the x, or 2 to the 8x. So again, I've been able to change the base of a exponential function by just tweaking the exponent on it. So the 256 had the exponent of x, the 2 has the exponent of 8x. Same trick for base 4. I can note that 256 is 4 to the exponent 4. Again, pulling out the fingers, we have 4, 16, 64, 256. So it's the 4th power. So now I can write f at x equals 4 to the exponent 4x. And finally, 256 is the same thing as 16 squared. So I can write f at x as 16 to the 2x. And graphing all of those functions in Desmos, or graphing them by hand for that matter, you'll see that all 4 of the functions, the original one and the ones with bases of 2, 4, and 16, all yield the exact same graphs. They're just different bases and different exponents. Okay, so what happens if we can't do this nice thing with, I can see that 256 is a power of 2 and a power of 4 and a power of 16. What if I wanted to do this as base 10? How would I do it then? Well, what I'm really trying to say is 10 to the exponent something is 256. And we already saw several times today that we can rearrange that using logs to get x equals log of 256 over log of 10. And by the way, log of 10 is just 1, because it's what power you put on 10 to get 10. So 256 log divided by 10 log, and it turns out that x is not as pretty as the others were, but 2.408, at least approximately. And we're going to know that anytime we do one of these, we're going to have a slight possibility of a rounding error. So once we've figured that, we can write f at x equals 10 to the exponent 2.408x. And that should yield the same thing. And again, you're welcome to go to Desmos, plug these in, and verify that that's true. For base 5, same trick. 5 to the x equals 256. Dyslexia is taking over. Take the log on both sides, and we get log of 256 over log of 5. And I'm getting 3.445. And so I can say that f at x equals 5 to the exponent 3.445x. And the last one we're going to do is base e. I mentioned this before. E it's called Euler's number. It's pretty important in calculus. And since this course is kind of the lead into calculus, I'm trying to expose it to you a few times. But it is just the number 2.71828. You'll talk more about its significance in the calculus course itself. But either way, e to the x equals the log, e to the x equals 256, jumping a step there. So x equals log 256 over the log of e. And even though I'm writing the e, when I punch it into my calculator, I'll punch it in as 2.71828. So 256 log divided by 2.71828 log equals 5.545. And so I could write f at x as e to the exponent 5.545x. I am going to pause for just 1 second and show you something interesting that might be of interest to you. Whether or not it actually is, I'm not sure, but we'll give it a shot. Okay, so what I've done here is I've just taken my function y equals 256 to the exponent x, and I made a little wee table of values in Excel just for a couple of quick x values, 0, 1, 2, 3, 4. So now what I'm going to do is I'm going to quickly do an insert scatter plot, which looks a little bit like that. Let me just shrink that a bit so it's a little easier to see on the screen. And what I can do is add a trend line, which basically is like a line of best fit, but it's a curve of best fit for something that's nonlinear. You can see that I can actually choose what shape I want for my trend line. So I could choose linear, but I know this is exponential, so I'm going to choose exponential. And it shows me what the exponential graph should look like. And then I'm going to choose display equation on chart. And I know it's small, but I want you to look at this carefully. This is the equation that it gives. Just make it a little bit bigger for you. Let's pump up the font size on that puppy. Okay, so what does it say? It says y equals e to the 5.5452x. Now the reason it's choosing e is because even though I made the function based on 256 to the exponent x, we've seen that Excel has no way of knowing that those numbers came from a base of 2 with an exponent of x. It could be literally any base. So Excel chooses base e for all exponential functions. And that's what, well, one of the better reasons that you should at least know what it means. If you're ever trying to make a graph in here and get its exponent out, you can figure out what the equation is pretty easily, but you have to understand what the e is. Now, if you want just something to the exponent x instead of e, just literally take e to the exponent 5.5452, punch that into your calculator, and what you're going to get out is a number that's pretty close to 256. Again, there might be some rounding error. In fact, if I do it right now, 5.5452, yeah, I get 256.00577. So pretty close. And then once you're there, you can use your knowledge of bases and exponential functions to convert it to whatever base you'd like, if you want it to be base 2 or 10 or whatever. But Excel only uses base E. Anyway, I thought I would point that out. Okay, so going back to our document, that's it. So there's some homework questions down there to give a shot. You've pretty much seen everything it takes to change bases. And the homework questions will show you a few examples of why you might want to switch bases to solve problems. Anyway, give those a shot and let me know if you have troubles, and I will see you in the next lesson. Okay, so what I've opened up here, oh, that looks weird. Hello. Okay, I'm going to have to edit that out. Why did it do that? Cell book 1.